Yes, we're ready. So my name is Renaud. I'm at @Views on Twitter, which is amazing because I got this handle like a month or two ago, and I was amazed it wasn't taken already. And anyway, I had the idea for this talk a month ago at the last Cocoaheads because when I got out of Cocoaheads, I walked with some people on the street, and I think you, mate, you talked to me and you were like, oh, you're like ex-Apple and you used to work on the Bluetooth team. Have you read the BlueBorne paper? And I was like, no, I didn't because it's behind me. But then I actually got curious and I read the paper and I realized, oh my God, like what happened in that paper is that the flaw that was revealed in that paper was actually code written by myself. And suddenly I felt a bit bad. I mean, this was not a widespread exploit or anything, but it was interesting. I found myself in a position that few people actually can be in, which is that you wrote code that is vulnerable and makes hundreds of millions of people vulnerable. And so the idea of this talk is really to talk about how did I get here? How even though I mean, I'll talk more about that later, but from a psychological point of view, how do exploits come to life? So it's not going to be really technical. It's mostly going to be about how did that happen. Anyway, so BlueBorne, did anybody read the white paper or look more than just like the headlines? Plus, of course. And then, yeah, that's it. So anyway, before I begin about BlueBorne, let's have quickly talk about me if you haven't met me or talked to me before. Obviously, I was instantiated in France, as my accent tells you. I was born there and I lived there until I finished uni. And in uni, especially, I was really passionate about low-level stuff. About kernels, especially. I have a couple of really silly patches for the Linux kernel at the time. That was really what I was passionate about, really understanding how computers worked. And that's important because I consider myself being really familiar with C. I have seen every C trick in the book. I know the language. I know that memcopies are bad. I know all of that. I'm not somebody stupid, and I feel like I know how these things work. Anyway, so in uni, I was really passionate about kernels, and that's what I studied most of my time there. And that led me to my first internship in my first full-time job at VMware in California, which was an amazing opportunity. I worked on VMware ESX and ESXi, terrible product names. Did anybody use these products at any point? No, it's pretty well used. So I worked on the kernel, so the virtualization hypervisor running on the actual bare metal, on the networking stack of these kernels. So yeah, like again, kernels, very lot of the stuff, some heavy C, every trick in the book, like I said, from 2007 to 2009. At the time where really virtualization was at its peak. It was, all the buzz was about virtualization. And then in some meetings, somebody sometimes mentioned somebody about the cloud. Maybe the cloud is going to be big, we don't know. Anyway, I left in 2009 just as I think the peak of virtualization kind of went down. So I left at the right moment. But that was an amazing experience. But I got an even more amazing opportunity, which is that I got hired to work at Apple. Specifically on the iOS Bluetooth team from 2009. I joined in August 2009, and if you recall these good few years, that was just after the iPhone 3GS was released, and iPhone OS 3 just got released as well, and we were just starting work on iPhone OS 4.
Is it colored? Is it colored inside?
No. I found that book on the shelf there. That's why I was like, that's amazing. So I joined in August 2009, and at the time we were just like the iPhone was still considered to be something that will drone in a couple years, and so we were not, working on the iOS Bluetooth team, we were not respected by the car manufacturers. They considered us a low priority compared to Nokia or Ericsson or anything like that. And so it was really an amazing, the opportunity of a lifetime to be able to work from 2009 to 2016 in that team and go from something that is unloved and that is not respected by the industry to something which is a core feature of the OS, because Bluetooth is part of so many of the features that Apple OSs are built upon these days, like the watch, the AirPods, and whatever else. So went from nothing to absolutely everything. That was an amazing time. And then after a while, after 7 years, it was time for a change. And so I actually joined the Home App team. Anybody uses the home app here? Okay, even less people. That's great. From 2016 to 2017. So as you see, like through my experience, I kind of like went through the layers. I started in kernels when I did system programming, and then eventually went at the UI layer. And yeah, I worked on the home app from 2016, from spring 2016 to 2017, and then the one that should not be named was elected president, and I decided that it was time for a change of scenery, and so I realized my lifelong, and so I decided to realize my lifelong dream and everybody's lifelong dream of joining itty bitty apps. I mean, that's even more mind blowing than everything I did before. Like I can't believe that this happened. So now, I'm like working with itty bitty apps. With the amazing people here. I got to know them over a beer a few years ago. I mean, I got to know Sean and a few other people, and that led to, one thing led to another, and suddenly you're in Melbourne. I mean, it's funny how it happens. Anyway, so that's about me, so that you know who I am, and you can come and ask me questions if you're interested in any story or anything. I have plenty. So the talk. Quickly, a quick overview of what I want to talk. First of all, what is BlueBorne? A lot of people are not really familiar with it. I'm going to quickly go over what exactly this flow represents. I'm going to ask, I mean, should you freak out? I mean, is there like a worm that, are your phones compromised right now by the Mossad or anything else? How did it happen? That's really the interesting part to me, which is like, I have insight, I have personal insight inside my brain as to how this happened. How did a flow that affects so many people, that could have affected so many people, went out in the wild? I'm going to talk quickly about what actually fixed it, because I have insight on that as well. And finally, some valuable advice if you ever find yourself in the position of writing an operating system for hundreds of millions of people. I mean, I know humble brag, but it's could be useful. What is not the talk? I am not going to talk about secret stuff about Apple. What I will talk about, I feel pretty comfortable talking about it. There's nothing secret, there's nothing confidential about it. But I'm not talking about any secret stuff. And anyway, I quit Apple like 6-7 months ago by now, and I don't know anything that hasn't been revealed by now. So at this point, I don't know anything secret that I will let slip or anything. So I feel good about that. I will not talk about the security policies at Apple. This is confidential. I will not talk about the processes that enforce policy. This is about Apple and not about that specific line of code that created this flaw. And I will not talk about why your AirPods don't work right. I don't know, Bluetooth is magic. I don't know how it works. It just works. Anyhow, so what exactly is BlueBorne? And so BlueBorne, obviously, like is a fashion nowadays, is like this fancy term that they invented for a flaw. Like there was Heartbleed, there was whatever else, and now there's like BlueBorne. They had a marketing name associated with it. And they made a little quick video about it. So I'm going to try to play it right now. And if it doesn't work, then we won't show it. But let's see if that will work. 3, 2, 5, 5. We're doing it live. All right. I don't know if we have sound. I hope we have sound. I haven't checked that.
Hold on, if you pause it, keep going.
Yep.
Oh wait, what phone have you got?
My phone.
No headphone jack.
No. No, iPhone 7.
I can't help. Wow.
Okay, never mind. When you can go.
Headphone jack, it would be.
Yeah, you can go on YouTube, and there's a little BlueBorne explained video, which is basically like I'm going to go quickly over it just to show you what it looks like. If my cellular connection goes, fancy animations, there's all of that. And then there's some CGI with some badly rendered characters, like a delivery guy that delivers a bunch of packages, but it's malicious, so he's infecting all your devices just as he delivers your packages. And you should be really frightened, and so a lot of marketing dollars went into advertising this security flaw, which I don't understand why, but this is pretty common nowadays apparently. So anyway, they have this video, you can watch it by yourself, and then I have to reconnect from this guy, so give me a second. And play. Oh, yeah, it works pretty well. So what is BlueBorne? Quickly, well, BlueBorne is it's actually a collection of vulnerabilities in different Bluetooth stacks. It's not just iOS or anything like that. It's actually just it's a team that spends some time say, hey, by the way, our Bluetooth stack secure, and they found a whole bunch of stuff because usually nobody really cares about Bluetooth until it's too late. Most of the vulnerabilities they found actually affect Linux and Android because these stacks, actually they share the same stack, which is BlueZ. And BlueZ has the same, has this vulnerability, so it affects mostly Linux and Android. I think there's like 7 flaws for this particular stack. But there's one iOS vulnerability also that they found, and they kind of agglomerate it into the rest. So the Android and Linux flaw are very much more dangerous, but they still bundle this iOS vulnerability together and say, oh, iOS is also vulnerable to that, even though it's totally not the same vulnerability. And it's way more difficult to exploit. And all of them, I mean, it's just all a bunch of bad mem copies. We know it happens. You just copy into a buffer, you don't check your length, and somebody cleverer than I am knows what to do with that stack, and make it actually do whatever it wants. Anyway, so in the paper, what I found interesting, for example, was this diagram, which is they analyzed the iOS Bluetooth stack with a tool, I guess, that analyzes the path of the data as it flows through the stack. So it's interesting to see your code that you're familiar with, but analyzed in such a way where it's visual, and that's basically how they analyze, what code paths are used in which circumstances and all that. And they have this neat visualization of where the data goes. And you can see, right, it's a Bluetooth stack is basically a network stack. It goes from the bottom, from the hardware, to the top where it talks to an application, for example, and you go for different layers, and it looks pretty neat. I found it was pretty neat to see a visualization of code like that. They say, so basically, and then they have this quote about the flow in iOS, which is that you can send a packet to a specific channel ID, CID, and think about a CID like a TCP port. It's basically a number that's representing a port. It says, okay, it's reserved for LEAP's single channel, and through its LEAP streams can be created to transport LEAP audio data, parentheses, presumably. LEAP is a LE audio protocol, and it's used by hearing aids. So this is a channel dedicated to hearing aids, hearing aid technology that we developed a few years ago, and it's still used by many hearing aids nowadays. Can anybody tell me what 0x2a is? Anybody recognize that number? No?
42?
It's 42, yes. So it's the answer to life, the universe, and everything. And so that's why it's 0x2a. There was no reason apart from that. So it's a magic constant that stayed there, and somehow it turned into the official port for that. So that's what they say in the paper. And then they disassembled the function in question, and they have an interpretation of the function from the assembly that they have. So at the top, you can see there's a C equivalent of what they see in the disassembly code. So you see here, there's an allocation for an audio chunk. Incoming packet gets copied into that audio chunk, and obviously there's no boundary checking. So if you have a length that is more than 0x68, then you basically override some bunch of memory you shouldn't be really touching. And then it passes that buffer to a callback. So they went through all this pain to analyze the assembly and kind of like figure out what the code looked like. Well, from my experience, I can tell you exactly what the code looked like, or at least something very close to that. And that basically looks like that. It's C++. I'm sorry to show you C++. I know it's late, and I know it's not the hour for that, but this was written in C++. And basically what you have is this function here, the audio callback, is basically the culprit, but it's basically based around an event system. So we had this event system at the time where you have a virtual class that is event that has to implement a function, a virtual function called execute, and then you define your event, which is a subclass of this virtual class, and you implement your thing where you store basically the data you want to carry over in that event, and you implement your execute function that actually does logic in that. And then in that, I have like private fields that basically stores the buffer and the buffer length. It's very raw code. It's not very good, but that's kind of what we use. We use C++ a lot, and we did things quite by hand at the time, which led to that vulnerability, because now you can see that when I look at the event with the operator new, it calls the constructor of the audio callback event, and this memcpy, which is in line, will copy the buffer to this buffer. And obviously you can override that quite easily. So to my recollection, that's kind of how it looked like. And that's how you get a vulnerability into hundreds of millions of devices. And it's a shame. I'm sorry. I have to say it at least. I'm sorry it happened. But the question is, should you freak out? Should you be really worried about that? First thing is no. You're fine. You're fine. So first of all, the main thing is that it's been actually fixed since iOS 10. And they say that in a paper. So it's only the only iOS version which is vulnerable to that attack is iOS 9. The daemon that has this flaw is heavily sandboxed, so it has access to some information, some data that is a bit private, but mostly it's heavily sandboxed, and it's in some aspects even more sandboxed than a typical app. So it cannot do anything you can think of. So there's a system behind the scenes that also sandboxes the daemons. Not only your apps are sandboxed, everything in iOS is sandboxed, even the Apple stuff. So if it gets compromised, it can only do so much damage because the process is sandboxed, in theory. Who knows? The Bluetooth packets are quite small in the end. You have to send probably a lot of Bluetooth packets to finally build the exact stack you need to compromise the thing in the way you want, and that's absolutely almost impossible. I don't know security people do that. I never understood it, but it seems quite impossible to me to actually use and exploit that flaw. And especially it's a heap overflow. It's not a stack overflow. So you cannot override the return pointer on the stack and all that. You cannot hijack the execution. To the best of my knowledge, you can only corrupt the heap, which makes it quite more difficult to actually do something meaningful with it. Again, I'm not a security guy. I'm not a specialist. Maybe you can do something really malicious with that, but it would be worse definitely if it was a stack overflow. And I would add to that also to these bullet points that in order to exploit that flaw, you need to know the Bluetooth address of the device you want to target, and that's also quite tricky to get because you need the device you're targeting to actually broadcast this address. Otherwise, you don't know that a device is even there. So you need to be able to listen to that address, connect to that address, and then send these packets through the layers. And then finally, all of that leads to the fact that there's no proof of concept. They say it in the paper, oh, it's vulnerable, it's terrible, and all that, but they say, because it's fixed, we didn't bother implementing a proof of concept that exploits it. So they could say the truth, or they could just also mean like it was too hard to actually implement something meaningful. So we just say that it could be terrible, but yeah. So that's should you freak out? And so I'm going to talk about how did it happen, how that vulnerable piece of code got written, which is really what interests me. And I'm going to go back again to the little code snippet that I have. So when you see that, right, like when you know that it's vulnerable, it's quite obvious. You're like, duh, there's a memcpy, and you definitely are copying a buffer with the input length directly without any bunch checking. This is obvious. And every time you see a vulnerability like that, you look at the code like, who's the toughest that wrote this code? This is so simple. And I was like that guy, and then it affects me. I'm like, okay, well, maybe there's more to it. So how did this happen? How did I end up? I think I wrote this code. I'm pretty sure I wrote this code. If not, I reviewed it, which makes me equally responsible. In either way, I feel responsible for it. So how did this happen? I think, to the best of my recollection, I wrote that code maybe 2-3 years ago. It's part of a feature, right? So when you're developing the feature, you're really concentrating on one thing. You're focusing on making it work. You are developing a prototype, and you're quickly trying to make something that works because you don't even know whether it's going to be successful or not. And this code doesn't matter right now. You're just trying to make something really quickly, to have other teams start using your stuff, and to unblock all the other teams that depend on your work. So your mindset is not security focused. So you're making it work, and you develop this prototype, And then this prototype code slowly turns into production code because you never come back to these lines of code. They work well. You never look at it again. It's a simple function. You write it once and then it's there, and nobody ever looks at that code again. It's stuck somewhere at the bottom of the file, and nobody cares about it. And then years later, you find out that somebody actually cared about it very, very deeply. This code also, in my mind, was designated to talk to a non-malicious accessory. It was not supposed to talk to anything in the world that could be anything. It was a very specific accessory, and I was not thinking at all about validating inputs because everything we did was based on a protocol specification. We had a specific, not really a document, but at least something that says this packet is going to be this length and it's going to be sent at this moment in this thing. And when you look at a specification like that, it kind of puts blindfolds on you where you just look at the specification and you don't really think about the bigger picture about what could happen if somebody doesn't follow specifications. So specifications are kind of harmful in that way, where they tend to narrow your field of vision and not make you realize that, hey, maybe you're not getting what you're expecting as your input. And also another thing that I did was that I really relied on the lower layers to do input checking. The vulnerability can be exploited because basically you can send that packet to that layer without having to pair with iOS, without having really to do anything to interact with it. And in my mind, I was really sure that some overlayer's responsibility would make sure that everything was fine, that the packet could not be bigger than a low energy Bluetooth packet, but actually it can be bigger than that. All of these things, I really put my trust into overlayers that didn't actually exist. And so I thought I was fine. I thought that was just pure application, business logic code, but that was not. It was a front-facing function that took unvalidated input from outside. And I didn't realize that at the time. If I did, I would definitely have written that in a different way. But to me, that's basically the most important point. I really thought that lower layers would take care of that. And that's probably what many vulnerabilities out there do, which is that they just trust some overlayer will take care of security. It's not my problem, it's somebody else's problem. But no, it's every layer's problem. And actually, this feature never even got shipped, but it remained enabled. This code remained enabled. This feature that I developed was not actually used in the end. We went another way to develop that feature. I'm not going to talk exactly about what it is. But in the end, this prototype code that never got anywhere, it wasn't used. It just stayed there. And and we didn't remove it. We just remained it enabled. And so that created the flaw. And that's a shame because that's really the stupidest reason for having a security flaw. Just I must say, this code path is now used for hearing aids, so it's not something that got removed. So quickly talk about what was the fix, actually. How did it get fixed? So in the paper, they claim this vulnerability was mitigated in iOS version 10. And that's a very, very blurry, abstract way of saying. I don't know exactly what happened. Because personally, I left the Bluetooth team in, let's say, April, May 2016. So that was obviously a couple months before iOS 10 was revealed at the dub of last year. And I personally never received a report about that flaw. I never got contacted by the team that reported that flaw. I never got contacted by my engineering manager. I never got contacted by the security team at Apple. So a few things may have happened, right? First one might be that the team that has this vulnerability never actually reported that to Apple. They never claimed that. They just say it was mitigated. They never said they reported it. So that could have happened. I don't know. I'm just theorizing. They could have communicated with the security team at Apple, and the security team at Apple might have looked at the code and found out that it was fixed, and therefore didn't deem necessary to contact the Bluetooth team and say, by the way, there was a flaw and all that. So that might have happened. I have no idea. I have no inside information about that. Or somebody else might have, somebody else might have known about that report. I don't know exactly what happened, but I personally never received a report about that flaw. So I don't exactly know what happened, what communications happened, and the timeline of everything at all. But the quirky thing about all this is that this was actually an accidental fix. Like, because I never get a report of that, there was never any like, oh, we need to change that function. No, we just fixed that in another way. And the fix was that when iOS 9 shipped and until I left the Bluetooth team, I was basically, one of my biggest tasks was to modernize the whole Bluetooth stack, because we're using, like you saw before, we're using like old C++ with bad methodologies and all of that. And I was like, no, we really need to embrace modern technologies. We have so much better now. And so let me go through the whole code base and start using modern Apple technologies all around, so that we don't have to write these buffers, memcopies by hand every time, which was a lot of craft, a lot of boilerplate, which I hated doing. And so I changed the function that you saw before into this. Instead of having an event, we just had now this notion of a byte buffer, which is basically like a ref-counted buffer of bytes, container of bytes. So you instantiate that with your buffer length. It allocates whatever you pass it, so it's always going to be the right size. And then you dispatch async to our work queue, so you use GCD, and then you use blocks, and this byte buffer gets ref-counted when it's copied into the block with C++ trickery. And then you call your async processing function, because we basically want to do that processing on a queue which is not the current queue, because current queue is basically the real-time queue where you want to send audio really soon. So you don't want to do most of this work on that. And by doing this modernization work, I collaterally fixed it. Like, there's no flaw anymore, and that's probably what happened, right? Like, when they say it was mitigated, it's not because we were aware of that flaw. It's just by the way, my modernization work just fixed that thing as well, and I did that work everywhere, and including that function. It was just a happy coincidence. But I'm sure that we would, if it was not the case, then we would have been notified by somebody and really fixed it in another way. But in my case, to my recollection, it was accidentally fixed. So yeah, that's the story of the BlueBorne iOS vulnerability. And so I can give you some closing words on some advice. Like I said, first advice, and I think we can all agree, avoid C++. I mean, there's really no reason these days to use this language anymore. There's few use cases for it, but we have way better languages now, including Swift, including Rust, including whatever else. I mean, C++ has passed its time, except some really like nerdy people that really like templates and whatever. Like, don't avoid C-based languages as much as you can. There's no reason nowadays to just use that. You have compiled languages that are performant, high level, safe, and that have the same characteristics as C++, so avoid it. Another one is that technical debt is evil. In that case, it's literally evil. It's not just like figuratively, because it actually creates security flaws. I know that we always say, premature optimization is root of all evil, and don't fix what's not broken and all that, but in that case, actually, that was beneficial. So there are instances where getting rid of technical debt both fixes bugs, fixes flaws, and makes your life better. So technical debt, I think we truly hate it, and it's up to you to really like allocate yourself some time during your project to just say, you know what, we're gonna revisit that, and we're gonna try to get to technical debt. I hope that you all work on projects where you spend some dedicated amount of time just refactoring some old stuff to make sure that you use the best practices of the day. It's always a good thing to have. Another recommendation is that, don't forget to fully disable features that did not make it into your app. I think last month, actually, we got a great talk from Stuart Gledo that talked about how to do that in an easy way with his nice feature switch. So make sure that if you don't ship something officially, make sure to completely compile it out or properly disable it so that you don't run into trouble later. And last advice, always spend maybe a little time. It doesn't take long, but spend a little time reviewing your code with a security mindset. Always look for flaws, look for memcopies, look for really stupid mistakes. I personally never did that, and I regret it. I should have done that. I should have spent a bit of time saying, hey, let's find something that doesn't look right. And in the end, it's my fault for not spending half a day just reviewing everything that I wrote and then like saying, okay, well, maybe there's something that doesn't sound right here. So if you're accepting arbitrary external input, make sure to always quickly, it doesn't take much. It doesn't take like a thorough review, but just think about it really quickly. Anyway, and that's it. So I'm open to questions now. Yes, it was mostly assumptions. Like you can extrapolate that to many vulnerabilities, which is like many vulnerabilities are based on assumptions. You're never going to get called through that context. You're never going to get called with that. Or like I said, some overlayer is going to take care of verifying that. And so you make assumptions and yeah, they bite you. They come back to haunt you if people look hard enough like they did with my code. Yeah.
Like when you said you fixed it accidentally, you may have fixed it accidentally, but you fixed it by applying a better pattern.
Yes.
Right. So in the case of like if you had a byte buffer type or something, where, you know, it's something that's managed in memory. It's like it's a high level abstraction that you have to write once, get that right once, and that solves every case of that potential problem.
Okay.
Right. If you apply that pattern or that type in every case. Right. So instead of having to check yourself every time you're using a string or writing a buffer or an array, you've got a high-level type which saves you from having to think about those potential issues in all of those cases. You have to think about it once if you've got it hard at that time where you're defining that one thing.
Yeah, and it was pattern identification, right? We knew for years that there was a lot of code duplication, a lot of effort to write this kind of event all the time. And for years I was like complaining, it's like, we need to do something about it, we need to do something about it. And finally I got enough time and enough runway to say, okay, let's take off technical debt and I'm going to dedicate my time to do that. And I was able to apply that thinking to patterns that I identified over the code. It's like, okay, we do that all over. Let's try to find one common, byte buffer thing, which is standard stuff, right? It's not like science or anything. It's not rocket science. So it's pattern identification. And use higher level patterns that are, that's what I can say.
How do you actually sort of start to understand what it is you should be looking for and all of these sort of patterns that may come about and lead to potential flaws?
Well, if it's simple, right? Like in a way, if you're parsing input or if you're copying input, then that's enough to capture 99% of what's going to be problematic. So in that case, it was really like obvious. It's a memcpy. You can grep for a memcpy and find the memcpy. Like it's a basic level 1 security flaw. It's not even like hidden beneath 10 layers. It's just like, oh, copy a buffer into another buffer directly with memcpy.
It's so common a flaw, in fact, that some compilers don't let you use memcpy anymore.
Yeah. That's in the first
I
place.
think two best pieces of general advice you gave were sanitize your inputs and
Yeah.
question your assumptions.
Yep.
Yeah.
That's really the root of all of this.
But that requires you to be really aware and to really think about it, right? It doesn't come like by mistake. No, it's just spend some time, dedicate some time, some reviews in your team or something. Says, by the way, like everybody's going to have to spend half a day in this release cycle to just like audit the code, whatever new code we wrote. Let's see if anybody can find something really stupid that somebody's doing, and let's fix that. And doing that will fix 99.9% of your potential problems, I'm sure. Like
the other thing is look into static analysis. So if you're not using plain built-in static analysis on your project, then you're doing something wrong. If you have access to other static analysis tools, use those. Look, if you're worried about your data parsing and sort of the input you take from the outside world, from whatever devices or network things you're doing, look into fuzzing on your parsing code. Basically, search for edge cases. Search for that buffer overflow.
yeah, fuzzers are amazingly good at finding flaws.
Yeah.
There is one thing called Open Web Application Security Project. So you're going to want to check that applies to web. But some of the things apply to application. For example, if you're working with SQL, like don't allow SQL injection on the other.
Commonly referred to as OWASP.
Yeah.
Okay. Yeah. Thank you.
Thanks for